Okay, so I was going to work on this problem. I know it's really challenging. So this is chapter 7, number 71, and we have two different cylinders, and they are connected together. So it says they are fastened together. But we have two different ropes. You can see we have one rope in the center here where around the smaller disc, and then we have one around the outer disc. We're given some very important information. We're given the diameter of each disc. Okay, so we need to make sure that we, in the beginning, go ahead and divide those numbers by 2 to account for the radius. And we are given the mass of each cylinder, and in the diagram we have the mass of each block. So let's go ahead and write down some information so we do not forget. What I'm going to do is I'm going to write down the mass, the radius here. I'm going to call this one R1, and that's going to be 1/2 of 10 centimeters, so 0.05 meters. So I'm going to call this M1. So M1 is, little m1 is 4 kilograms. Okay. If you want me to, since it's hard to see if it's a capital letter or not, I'll call it M disc 1. Maybe that'll be easier to see. This is 5 kilograms. Okay. And this is the radius here. So R2 is going to be 0.1 meters. And the mass of that disc is 20 kilograms. And call this M2. Okay, so now that we have that out of the way, let's determine some important information as far as they're fastened together, which means that they will rotate together. So they're going to rotate in the direction of net torque. Okay? And we really need to determine this as soon as possible in order to really do this well. So I want you to think, which force is going to be causing the most torque on this system? Because we have two discs, they're connected together. So that's going to be, our system is going to include both of the discs and both of the masses, the hanging masses. So is a 2.5 kilogram mass with a radius of 0.1 meters going to cause more torque than a 4 kilogram mass at 0.05 meters? Okay? Well, remember, they're both circular. Okay, because it's a disc, which means that the torque will always be at a 90-degree angle. So just kind of think to yourself, a 2.5 kilogram mass, if you notice, the 2.5 kilogram mass is 2 times as far from the rotating axis. And M1 is not 2 times M2. So M1 is less than double the mass of M2. Okay? So that's going to tell me very quickly that there's going to be more torque caused by the hanging mass M2 from a larger radius. So that ultimately means that this will rotate this way, which means that our alpha will be this way, our net torque will be that way, etc. Our net torque will be that way. It also tells me that this is going to accelerate downwards, and this will accelerate upwards. Okay, so I wanted to determine that immediately. We will move on. Okay, so in order to keep this video short, I did a lot of the free body diagrams for us already. Let's look at the one for M1 and then M2. So those are our two hanging masses. So the only forces acting on them are tension and weight. If we go back to our picture, remember that we said that M1 is going to be accelerating upwards. That's the mass on the smaller disc, the 4 kilogram mass. That one's going to be going up, where M2 on the larger disc is going to be going downwards. So I put the direction of acceleration here to remind me, which since it's going up, that means this is a positive value. Since it's going down, this is a negative value. So all I did was I looked at my Newton's second law equation, and for M1 it is T1 tension minus M1G, and acceleration is upward, so I set that equal to M1 times A. And for M2 it's T2 minus M2G, and I set it to minus M2A because acceleration is negative. Now ultimately what we want to do here is we're going to want to solve for tension, and I'll let you know why. Okay, we're going to want to solve for tension because if we now move our eyes up to the discs, it is the tension force that is causing the torque. Okay, so what we need to do now is we need to look at each disc, and we're going to find the net torque here in the next few steps, but we need to individually decide, is T1 causing positive or negative torque? Well, if T1 and disc 1 was the only thing in our system, it would cause it to rotate clockwise. Okay, which means that this is negative, causes negative torque. Okay, so my torque here, tau 1, is going to be a negative value. So I'm going to go ahead and put that in there. And that torque is just going to be the perpendicular force, T1. It's a circle, so it's always perpendicular, times R1. I just decided to capitalize it, okay, to make things a little clearer. So that is torque 1. If we look at disc 2, this force is going to cause it to rotate counterclockwise, which means it is positive. Okay, so tau 2 is just T2 times R2. Okay, so whenever we have a rotating object and objects moving linearly, we're going to need to relate the angular quantities to the linear quantities. So what that ultimately means is that we're going to use a substitution. Okay, now the whole point of this problem is we're trying to find alpha. Okay, and so just to remind you guys, alpha, the way we're going to get alpha is we're going to look at the net torque, and then we're going to look at the moment of inertia for the two discs combined. Okay, so we're working on our way to get the net torque. Well, what does the net torque depend on? The net torque, as you can see, depends on the tensions, T1 and T2. So we're going to end up finding T1 and T2 from these linear equations down here. But we have a big issue here because right now these are written in terms of linear accelerations. Okay, this is one system. Remember, they're attached together, so they're going to accelerate together. So what that means is the acceleration for each one is going to be the same. Okay? So what we need to do, we can sooner rather than later, we'll make this easy, is we want to convert our linear accelerations into angular accelerations. Okay? And then we're going to want to solve for t1 and solve for t2. So what I can do is I can write this as m1 alpha r1, and I can write this as minus m2 alpha r2. Okay, so now I'm going to go back up and solve for t1. So t1 will just be m1g plus m1 alpha r1, and t2 is m2g minus m2 alpha r2. Okay? Alright, so we have our two tensions. Let's now go and look at what our net torque would be. So remember, net torque is just going to be tau 1 plus tau 2. Okay, and let's remember that tau 1 is negative, tau 2 is positive. So what this is negative T1 times R1 plus T2 R2. Okay. I'm going to rearrange this just because it's easier for me to think of it as this. It is the exact same thing, so this is not a necessary step, but to me it's easier to think of this way. Okay, so what I'm going to do now is I'm going to insert what we saw for T2, which we have M2G. Also, I'm going to move R2 in the front of the parentheses. Okay. Just because that's usually how you write things in your math class. So M2G minus M2 alpha R2 minus R1, and T1 is M1G plus M1 alpha R1. Alright, so we've done a great job. We've written our net torque. We have the next thing that we need to find out is the moment of inertia for the entire system. Okay, so they're both disks. Okay. Which for a disk it's 1/2 mr squared. Okay, or mr squared over 2. Exact same thing. So that's just going to be the moment of inertia of disk 1 plus the moment of inertia of disk 2. Okay, which is m d1 r1 squared over 2 plus m d2 r2 squared over 2. Okay, so this entire thing is the moment of inertia for my whole system. Okay. Now, I think it's what we're looking for is alpha, which alpha is torque over the moment of inertia. I think it's going to be a little bit easier right now to write things like this. The net torque is equal to our moment of inertia times alpha. So alpha is what we're ultimately looking for. We just found the net torque, and we just found the moment of inertia. So now I'm going to bring those over here. So I'm going to substitute them. So we get R2 M2G minus M2 alpha R2 minus R1 plus M1 alpha R. And if I have enough room, yep, so all of that, so this is the whole left-hand side. I'm just bringing it down here because I'm running out of room. ND1 R1 squared over 2 plus ND2. Okay, so that's all I did. I will put this all in brackets for now, just so we remember. So believe it or not, we have all the physics of this question done. The entirety of the remaining part of this question is all algebra. Okay, physics got you this far. Now you have to rely on your math. And remember, we're looking for alpha, but the big issue here is we have an alpha here, and we have an alpha here. So clearly, we cannot just divide by our inertia of the entire system, because we would have alphas on the other side of the equation. So what I'm going to do is I'm going to distribute these. Okay, so I'm basically going to expand those, and I'm going to expand that. And what that's going to help me do is, number one, whenever I expand the left-hand side of our equation, it's going to allow me to move the variables with alpha in them to the right-hand side of our equation, and then simplify the left-hand side of the equation. Okay, so let's get started. So if I move, so the left-hand side equation will become the following: M2G R2 minus M2 alpha R2 squared minus M1G R1, and please be very careful. Remember, you have to distribute the minus sign here as well. So minus M1 alpha R1 squared is equal to MD1 R1 squared times alpha over 2 plus MD2. Okay, so let's remind ourselves with alpha here, 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 and here. Notice that all the alphas on the left-hand side are a negative quantity. So it's going to be really easy to just add them to the other side. Alright, it's going to be exactly what I'm going to do. I'll write it in green so it's very clear. We're going to add those on this side. Okay, so in order to save time, I just wrote the next step, which was just adding those quantities to the right hand side, and you can see our result. We have alpha here, 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 and here. That's excellent news. We have alpha in every single term, which means that I can pull it out. Okay? If I look on the left hand side, I have G in both terms. Okay, so the next step is going to be on the left hand side. I'm going to pull out G, M2 R2 minus M1 R1. Brilliant. And to make this easy to see, we will do this in 2 steps. So I'm going to pause and it'll show you the answer. Okay, so on the right hand side so far I only took out alpha, but if you look, I rewrote the right hand side slightly differently by just writing the quantities with R1 near each other and the quantities with R2 near each other. And so what I want you to see is I'm going to essentially pull this out between these first 2 quantities. So we're going to have some parentheses there and do the exact same thing here. It's going to make things look a little cleaner and a little bit easier when we do some division. Now, it's not completely necessary. We have enough information to completely just divide, but it does look a little messy right now, I will be honest. Okay, so that's what I did. Now, some of you may argue this looks worse. That's totally fine. But this is how I solved for it. So we can see that we're going to take the radius 1 squared and multiply by half of the mass, by the quantity of half of the mass of our disk plus the hanging mass. And we're going to do the exact same thing for R2. And we're going to add both of those together, and that's equal to alpha. So, or is being multiplied by alpha. So at this point, we have the left side of the equation, and we have the right hand side of the equation. So all I need to do now, we're almost done, is just divide by this whole mess on both sides. Okay? So let's write that. Now, I'm just going to write alpha on the left hand side. I hope that doesn't bother anybody. Doesn't change anything. Oops. So alpha is equal to G times the quantity M2 R2 minus M1 R1 over R1 squared MT1 over 2 plus M1 plus R2 squared Okay, we are ready to do some math. Now I hope that you can look at the beginning of this video and plug in the values. Okay, because we were given all of the other information. We're given M1, M2, R1, R2, the mass and the mass of each disk, and obviously you know A. So I will tell you what you should get. In the numerator, you should get 0.98 meters per second, meters squared, second squared, be your units. And in the denominator, you should get let's see. And I hope everyone makes fun of me because I wrote the wrong answer the first time, because I did not correct my work from the past. So you should get 0.49 in the numerator and 0.141 in the denominator, giving you 3.46 radians per second squared. Now, this is a great question. I hope you enjoyed it. It's possible to have something like this on an AP exam. Most importantly, the reason why this is such a good example is it tests concepts of relating linear to rotational motion. We had 2 different ropes, 2 different cylinders, 2 different masses. Okay, we had to be very careful about the direction of our linear acceleration and the direction of our torques, determining which direction the system was going to rotate. Okay, all in all, those are the most important things to take away from this question. The algebra at the end, yes, is a little annoying, but you should be able to do it. Once again, I do recommend solving things algebraically first, because if you make a mistake, it can be a little hard to determine. Okay? Alright, make sure you watch this. Hope this helps. Bye-bye.